go. So we're picking up right where we left off. No time to waste. We're going to inheritance. This is the 5th lecture out of 10. So after today, we are 50% through with the material. What we just had was the problem set 0 deadline, which y'all did overall pretty good on that. Really well. For those who like stats, I don't have the exact stats pulled up, but most of the class did really well. The lowest legitimate score was a 40, except for 4 students who didn't even bother to make a submission. I don't know what's going on with them. If you're one of them, you're way far behind already. But most of y'all did either 40 or better on this deadline. A few of y'all submitted right after the deadline, the next day, I think. And yeah, the next day got the 20% hit, but still were able to finish it and get most of the points. We are at the point where you can do everything with problem set 1. We've actually been at that point for a week. After last Tuesday's lecture on classes, you had everything you needed for problem set 1. So that deadline's coming up. It's in 2 days. Make sure that's on your radar. Come to office hours if you need help. And the linked list and inheritance problem set 2, you'll be able to do that after today's lecture. So if you do want to start getting ahead, which summer moves extremely fast, you should be wanting to get ahead. After today, problem set 1, problem set 2, you can finish both of those and be on top of the material. And then it'll be a while before we get polymorphism, trees, and testing. We need the next 3 lectures to be able to do this one. And then graphs for the last homework. Okay, with that, I don't think I have really anything else to talk about. Let's get into inheritance. So this is inheritance is an OP topic. So that's object-oriented programming. So we already learned about classes and objects, how to create objects using our classes, and we want to take that to, wrong shortcut. And we want to take that to the next level with inheritance. So it's not always, let me reword that, it's often convenient to have more functionality than just creating classes and creating objects of those types that we defined with the state and behavior of that type. Sometimes we want to share functionality between multiple classes, and that's what we're going to do with inheritance. That's our goal, is to write code one time and have that code be used in multiple other classes. So we're going to do this through example. I think inheritance is best taught through example. A lot of the 116 topics, I believe, are such topics. So we're going to simulate a small piece of functionality for a would-be game. We're not going to build the full game. In the fall and spring semesters, we do have a game features assignment where you work on this huge project. It's a bit overwhelming, especially for the summer going so fast. But we are going to simulate a game that has health potions and weapons in it. We have these 2 different types of items that a player can interact with. So let's just jump right to some code. I want to create a health potion class because I want health potions in my game. So we're going to have a health potion class with both state and behavior. The state is a collection of instance variables. These are the variables that are declared outside of all of the methods. For our purpose for a health potion, I want a variable that keeps track of the amount of health that will be recovered when a health potion is consumed, which we're calling increase here. Not super fond of that name, but well, I didn't change it either, so living with it. But increase the amount of health that will be increased when a potion is consumed. And then an X location and Y location, so we can have a health potion exist in a 2D world. And I always think of a top-down, like grid-based game with this, where each item is going to have an X and Y coordinate, and then you can walk to that location to be able to pick up a health potion in this game. And then if a player uses the health potion, they're going to be healed a certain amount based on that instance variable, the increased instance variable. And this is just simulated with a print line. We don't have to get too lost into all the functionality and how this would incorporate into a larger project. But we'll simulate the player was healed, increased number of HP. And then we have a constructor to initialize all 3 instance variables. Constructor doesn't always have to take every instance variable as a parameter, but in this case it does. The constructor is all 3 instance variables as parameters, and then assign all 3 of those instance variables. and that's our health potion class, which, great, but like, we already knew how to do all that. That's just classes. We already created classes. We did constructors. We did instance variables. We did methods. We did the keyword this. We did public versus private. There's nothing new on the screen right now. You all should be experts on this by now. And I know I say things like this a lot, but if you're not an expert on what's on the screen right now, you are behind. You're risking falling way too far behind for a 6-week course. This was a full week ago, which is effectively 2 weeks in a regular semester. You'd be 2 full weeks behind. You can't do that and expect to do well in the course. So you need to be an expert on this. The rest of the lecture, I'm going to just assume that you are. And if not, you might want to rewatch last Tuesday's lecture. So we're already experts on everything that's on screen. So what are we doing today? Of course, the title of the lecture is Inheritance. We're going to talk about inheritance. So let's talk about inheritance. And what the hell it even is. Like, what is inheritance? So inheritance gives us a way to be able to borrow or inherit functionality from another class into a class. So if we inherit all of the functionality, we're going to get all of the state and behavior of one class added to another class without having to duplicate all of that code. This is what it looks like, but let's break it down in quite a few slides. This is new content, so I'm going to do it in quite a few slides here. So first we created a brand new class, this game item class. And my goal is for the game item class to keep track of anything, any state and behavior related to every game item in my game. If it's common across all game items, it should go in the game item class because that's what all game items do. In this case, in this example, I'm going to say that's location. Every game item in my game has a location. And we're going to represent that with 2 doubles, an X coordinate and a Y coordinate in 2 separate doubles. That's what a game item does. It has a location in the game. And it doesn't matter what type of game item I'm going to have, it's going to be somewhere. It's going to exist in the game at some XY location. And then I'm going to extend game item. So when I create my health potion class, I'm not putting all of the code in health potion like I did before. Instead, I'm going to create health potion and use this syntax of extends game item. That's our syntax to inherit from another class. If I say health potion extends game item, what I'm doing is saying give me all of the state and behavior of the game item class and put it in the health potion class. This is almost exactly as if you copied all of the code inside the game item class and pasted it inside the health potion class. There are quite a few nuances. It's a little bit different than that, but it's, for the most part, that is what we're doing. We're taking all the state and behavior of game item and stuffing it into the health potion class. And then in the health potion class, we're going to add more functionality. We're going to add the health potion specific functionality, being the increase instance variable, initializing that variable, and then the use method that's going to be able to actually heal the player when they consume a health potion. So extends is our keyword to get all of the state and behavior from one class into another class. So all of the state means all of the instance variables of the class that you're extending are now instance variables of the extending class. So health potion extends game item means when we create a health potion on the heap, when we say new health potion, we don't just get the instance variables of the health potion class, we also inherit the instance variables of the game item class. So when I say new health potion, I create that health potion on the heap. It's still going to have these 3 instance variables because it got X location, Y location from game item and also contributed its own increase instance variable. So it gets all 3 instance variables by going through the inheritance through the keyword extends. And we don't have to put that in the health potion class. We just get it because we said extends game item. We get all game item instance variables. We also get all of the behavior of the class that we're extending. At this moment, it's just the constructor, so we don't really have anything to it. Actually, it is pretty interesting. But any methods that are defined in the game item class, we also get access to those methods. So we have a game item constructor, which actually will be very important. You'll hear me talk about this a lot throughout this week, today's lecture and the polymorphism lecture. I will talk about superclass constructors. For now, let's just say this will be important, and when we get to it, we'll discuss it at length. First, let's get a little vocab because I just said the word super, but I haven't defined that yet. And no, I didn't forget about this line. This is very important as well. But we got to get this vocab out here because I'm going to use these terms throughout the rest of the semester. When we have a class that extends another class, we say that the class that it extends is its superclass, or sometimes you'll hear it called its parent class. And when you go the other way around, we call, in this example, health potion is a subclass of game item, and it is a child class of game item. So game item is the parent class or the superclass, and health potion is the child class or the subclass in this inheritance relationship when we say health potion extends game item. I don't know why I'm like this, but when I'm talking about the superclass, I will use super instead of parent. And when I'm talking about the child class, I'll usually use child instead of subclass. So I kind of mix the two, the superclass and the child class. Just the vocab, probably whatever instructor taught me this to begin with, that's probably what they did, and it just stuck in my brain. But I will mix those a little bit. Out there in the real world, you will hear people use all four terms, super, sub, parent, child. So just being aware of what they all are is important. You know they're talking about inheritance relationships. Just a question regarding the midterm, what all topics are coming, and is there any trace practice? We will provide trace practice. We don't have it available yet, but I think it's absolutely reasonable to give some extra trace practice. The OOP quiz, we can jump to the website real quick. The OOP quiz is inheritance and polymorphism, and by implication, it will also be, It will also be, so inheritance and polymorphism for the OOP tracing. By implication, that will also cover classes and objects. We will be creating objects on the heap. You do have to know how to go through constructors and everything, but it will also include inheritance and polymorphism. So after Thursday, you'll have everything you need for the OOP tracing, and we'll get some practice problems out so you can start looking at those. You don't really have what you need to trace either inheritance or polymorphism quite yet. There's just a few things I have to talk about in these two lectures. And then for data structures, it's going to be linked lists and trees. And we haven't gotten to trees yet either, so I could give you practice right now, but actually you could probably intuit how to trace through a tree, if I'm being honest. You could probably do this one right now if you fully understand all the tracing we've done so far. Trees is a lot of references and some fairly complex recursion. But if you treat recursion as a regular method call, you could probably do that right now. But we're getting to the point where we're about to have all the concepts covered for the midterm, and then it'll be a higher priority getting your tracing practice out. Practice questions will go on Piazza. We'll do a pinned post on Piazza with some practice questions. And speaking of the tracing on the midterm, one of the biggest, I shouldn't say the biggest, no problem. One of the biggest things we're looking for, actually I'll just say the whole thing. There's two things we're looking for when it comes to the inheritance traces, and if I'm being honest, we don't actually add anything for the polymorphism traces. When we get to Thursday's lecture, I'll really emphasize that point. There's really nothing new that you have to do in your traces for polymorphism. Polymorphism is more of a programming concept. We'll get you in the problem sets with that. But there's nothing new for tracing polymorphism. There's one key point, and I'll make the big point of everything with polymorphism, you just ignore it when you're doing a trace. That's really what it comes down to. The two things we're looking for inheritance, so the two major things we're looking for in the OOP trace is one, making sure your super constructors are called, which is what I'm about to go through on this slide, and then two, when a method is called, which method is called. You'll hear me say both of these things multiple times. As long as you're paying decent attention to lecture, there's no way you can miss it because I repeat these things so many times. You're going to get sick of me hearing it, and then when the midterm comes, there will still be people who miss their superconstructor calls, and then I say, I don't think you ever watched a lecture. So superconstructor calls. The superclass constructor is always, 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 100% always called when you have an inheritance relation and you create an object of the child type. So if I say new health potion in my code, I'm calling the health potion constructor, and the first thing that the health potion constructor absolutely must do 100% of the time is call the superclass constructor using the super keyword. Super is a keyword that, for the most part, you can think of as being replaced by the name of the superclass. So this is like saying game item, X location, Y location. We're calling the game item constructor right here. Now notice that we're calling the constructor, but we're not using the keyword new. So this is a very special case of a constructor call that isn't creating a new object. That's why I really emphasize that your hint for that is if you see the keyword new, you're clicking new object on the heap. If you don't see the keyword new, you don't click new object on the heap. I emphasize that way mostly so when we come to superconstructor calls, you don't have to think, oh wait, that's a constructor call. I'm creating an, nope, you don't see the keyword new, you're not creating a new object. You will be creating a new object because somewhere else in the code, not shown on screen, you'll have new health potion double int. And then the health potion constructor makes a second stack frame for the superconstructor call, which always, always, always has to happen, and it's the first thing the child class constructor will do 100% of the time. At least I should qualify, in Java. This is a Java, might be true in any major language, but definitely in Java, the superconstructor is always, always called. So we have two constructor stack frames that are going to go on the stack to create a single object, a single health potion object. So we have to call the superconstructor because that constructor is going to have to initialize some instance variables, its own instance variables. We need that constructor to be called, and Java doesn't give us an option. It will be called 100% of the time. Now, if you've written code in Java before and you've used inheritance, you might have seen code like this, changing up the example a little bit, where the game item constructor just initializes to some constants. It doesn't take any parameters, and I don't have a superconstructor call right here. Health Potion doesn't explicitly call the superconstructor, but the superconstructor is still called. So in the special case where you have a superconstructor that doesn't take any parameters, you don't have to type super open parenthesis, close parenthesis, semicolon. You don't have to type that line. You can, optionally, it's still fine to have there, but Java doesn't force you to type that line of the superconstructor call right here. It just knows that since the superclass has a constructor that doesn't take any parameters, it knows that you don't have any choice. You have to call the superconstructor, and there's no choice for you to make. You don't have any parameters to choose, so it's just going to call it for you. It's just going to say, hey, yeah, the one with no parameters. That's what you literally have to do here. I'm just going to call it for you. So Java's got our back there. It doesn't make us type that extra line, but it does still happen. So if we were tracing through this code and we have new health potions somewhere like in a main method, we do have to still put the game item constructor on the stack. For the traces, I don't really like doing this. I think it's a bit of a trap question. So I like to have them explicit in the traces for the midterm and final. But if you do see code, like we'll see code like this in lecture quite a bit, the superconstructor is still called. Okay, and that really is inheritance. That's what I like to do is at the beginning of each lecture, I'll give you everything you really need to know. Like that's inheritance for the most part. Well, we didn't get to overrides yet, but that's most of what we need to know. But we need to, one, reinforce this. I got several memory diagrams, 2 memory diagrams we're going to go through today. We're going to reinforce this a lot. But I also want to motivate why the hell we would ever do this. Because what's on screen right now is really dumb, right? Like, you would never write code like this. You should never write code like this, what we have right here. you would put all of this functionality in the health potion class and just call it a day. There's no need to split this code across two classes. Now your code, your functionality is split across two files, making your code harder to read. And anyone reading your code has to understand inheritance. You have to understand inheritance to write the code. It's just a lot more complexity to do the same thing that we did in a single class earlier. There's no reason to ever do this. But where this does give us an advantage is when we have multiple child classes. So remember, in our example, we're going to do health potions and weapons. If we just had health potion, just one type of game item, inheritance doesn't make sense. Don't use inheritance when there's only one child class, unless you have a really good reason to. I would be surprised to see an example where that made sense. But when you have multiple child classes, now we really get the benefit of inheritance. If we have weapon and health potion both extending game item, now health potion and weapon both get all the state and behavior of the game item class without having to duplicate any code. Because this same code without inheritance, all of these two instance variables and initializing those instance variables has to be copy and pasted in both of these classes, which gets hard to maintain. A big thing, especially with the OOP side of this course, big part of OOP is making your code easier to maintain, so it's easier to add new features to your game. So when I want to add a new game item type, what I want to do is what I want to do is extend game item. That type gets everything from the game item class. That defines everything that a class needs or an object needs to be able to be a game item. In this example, it has a location in the game world. That's what we want. So when I create a third game item type, I just want to say extends game item. It now has everything it needs to be able to be a game item in the game. And then I only have to worry about the behavior specific to that class. When I'm creating a weapon, I only have to care about how a weapon is dealing damage to other to enemies in the game. That's the only thing I'm worrying about. What happens when a player uses a weapon? And then we have this instance variable to keep track of how powerful that weapon is. With health potion, how much health is going to be recovered when we consume a health potion. And our game item class is pretty small right now, but this would grow. Like I can't fit much more code on the screen, but we would have a lot more functionality in the game item class to really make this worth it. For one, you can imagine a move method. So I don't just want my game items to exist in the game world. I want them to be able to move around in the game world. I'm also eventually going to want a physics engine that applies to these. So if, say, a player throws a weapon, or one of the weapons, maybe we have another class that's a bow and arrow, and they fire the bow and arrow, now I have an arrow game item that's moving in the game world and has certain physics applied to it. I can put all that information, all that code in the game item class. Eventually we would put that in a separate physics engine class, but we can put that in the game item class and then have every game item just naturally inherit all of the physical behavior, moving through the game, gravity being applied. If we want nice parabolas for all of our game items, we don't have to copy and paste that code into every single game item that we have. We can put it in the game item class, and all our game items just inherit that code without us really having to do anything. We write the code once and reuse it in many other classes. And this is pretty nice with two classes here, but what happens when we have hundreds? What happens when you keep wanting to add more and more item types to your game? You're going to keep adding new and new classes with very different behaviors that they're defining, but they'll all share the game item behavior because they'll just extend game item and get all of that location behavior or anything else that needs to be common to every single game item. So this is at least the first advantage to inheritance, is we get to share code across classes. If we have any classes that have a lot of similar behavior, we can factor out that similar behavior, put it into a common superclass, and then extend that superclass to be able to share that state and behavior. So this is why inheritance makes your code much, much easier to write when you want to expand your functionality. If you want to add bow and arrow to your game, if you don't have the game item class, that can be a bit tougher. At the very best case, you have to cut and paste a lot of code to be able to do that. You're going to one of your game item classes, copying a bunch of code and pasting it into the new project, which gets annoying when you have, say you do have 100 different game item classes in your code, and you want to make an update to the way your physics behaves. You want collisions with walls, you want the objects to bounce off of them based on some buoyancy instead of just hitting the wall and falling. Maybe that was your initial behavior. You want to make a change like that, you got to make the change, copy it, and paste it 99 times. We're not going to do that. Nobody's going to do that. Kind of like when you first learn loops. Like, we're not going to do that. That's tedious, that's annoying, and you're inevitably going to miss at least one of those object types. And now one of your objects is colliding with walls and just falling, while the rest of them are bouncing based on some buoyancy. That's a very hard bug to find when you have such a large project. It's going to be very difficult to trace that one down. So we share the code with inheritance, and then we don't have mistakes like that. It's a lot easier to write bug-free code. All right, let's start tracing this. So we don't have, wait, is this true? No, we do have. Use. I was going to say we don't have everything we need, but we do have everything we need. What are we doing? Object. And I just talk about it without tracing it yet. Okay. And we have one print line. I think we can get it right like this. Okay, so let's trace through one of these things. I have 3 different classes here, so when you go to the repo, there are 3 separate classes if you want to look at the code itself. But I have the text document just so I have all 3 in the same file. It makes it easier to paste into the tracing tool, just so the trace is all set up without watching me copy and paste 3 separate files. Kind of the advantage of inheritance itself. So let's start with the main method, just like every Java program. We have a main method. The main method is going to create a variable weapon. I see new. Keyword new means I'm clicking this button. I'm creating a new weapon. That part hasn't changed. I'm going to create a constructor for weapon. It's going to return to the weapon variable. This, I rolled OX100. And I have arguments. Let me get the arguments on here first. I don't know where they're going yet. I haven't looked at the code yet. But I do know my arguments, which I often do like to do. Get everything I know first before I crack into some more code. But I'm calling the weapon constructor. So I'm creating an object of type weapon. Let's get the parameters. We know what the parameters are now. X location, Y location, damage. Whoa. Y location, damage. And when we create this object on the heap, it's going to get a copy, just like our other classes, going to get a copy of all of its instance variables. So we have damage. But then we get to our first new thing. We see that we extend game item, so we also have to go to its superclass and grab all of the instance variables from the superclass. So X location, Y location are also instance variables of this weapon object, because it inherited these instance variables from the game item class. So now we got all our instance variables, all our constructor parameters, all our constructor arguments, and all of that. We're ready to actually run the constructor, and the very first thing we run into is this super constructor call. Whether this is here or not, we have extends some class. The super constructor call will happen. Here it's explicit and it takes parameters, X location, Y location. So we have a super constructor call. I don't see the keyword new, so I'm not creating a new object. This is a constructor call that's not creating a new object. So what we do is look at the super type. It's game item. So we're calling the game item constructor that takes 2 doubles. So we're calling this constructor right here. This is our super constructor call. So this is another method call. Happens to be a constructor, but it's a method call. So we get a new stack frame for the game item constructor. And that's a non-static method. It's a constructor. It will have the keyword this. When you have a super constructor call, this is still a reference to the single object that's being created. So here, my this keyword is OX100. So the child class constructor will forward the keyword this, that context of the object being created, it'll forward that to the super constructor. Super constructor has two arguments. We gave it X location, Y location from the weapon stack frame, 3.9, negative 0.5. And those parameters are X location, Y location. Nice and consistent. And then we run the constructor. As long as we have the keyword this set up properly, the way it's supposed to be, you read through this code just like any other non-static method call. This dot X location equals X location. It's a new expression on the right-hand side of the assignment operator. So this is from the stack frame. We start over in the stack frame for each expression. X location resolves to 3.9. So 3.9. And then this dot Y location equals Y location negative 0.5. And that constructor is done. That brings us back to the weapon constructor, and we can finish initializing this object. This dot damage equals damage. So we have 10 for our damage variable. This returns, constructors return a reference to the object that was created. And we have our first constructor call that calls a super constructor. We have two constructors that went on the stack. They only created one object though. So the super constructor is there to help initialize its part of the object, all of the parts of the object, the state, the instance variables that were inherited from that superclass, but it doesn't create another object. We don't create an object of type game item when we hit that game item constructor because, well, we don't see the keyword new, but also that's just not how super constructor calls work. Okay, then weapon.use. So weapon.use, we're calling it from OX100. So this is OX100. And this brings us to the next point of inheritance and really the rest of the OOP trace for the exams is which method is called when a method is called. For this, we're going to go through what I call our progressions. We're going to always start the way we have with just objects and classes. We're going to start the same way. We're going to look at the calling object. So use was called from the object OX100. And by the way, for this example, there's no way to get it wrong. Use, there's only one choice. Move, there's only one choice. But I want to go through how this works because in the next trace, there will be multiple choices and you'll have the opportunity to mess it up. So we're going to go through how Java resolves these method calls first, and then we'll get into the more complicated examples. So it was called from OX100, which is an object of type weapon. So we look in the weapon class for a method named use that takes no parameters. And we find it right here. So that's the method that's called. That's what we've always done ever since the party and character example, where each class had a win battle method. Which win battle method was called depended on the type of the object that called the method. So same thing here. Use doesn't take any parameters. We just print to the screen. Damage dealt. This dot damage is 10. And the method call resolves. And we move on to the move method. So we have another method call, move. This, it's called through weapon, so OX100. We're going to do the same exact thing. We're going to look, actually let me get my arguments first, get that out of the way. We don't know what the parameters are, we haven't found the method yet. But this is of type weapon, so we're looking in the weapon class for a method named move that takes two doubles, and here we don't find the method. We always start our search in the class matching the object type. The object type, always the object type. We start our search there, and we don't find the method that we're calling. So this method doesn't exist. We can't call this method. Well, this is where inheritance kicks in. If and only if you do not find the method in the class matching the type of the object, then you go to the superclass and continue your progressions. You're going to progress through the superclass until you find the method. So we're going to go to the game item class. Only because we didn't find move in the weapon class, we're going to move to the game item class. We do find the move method right here, and this is the method that's being called. So we have dx dy. We have this dot x location. I got the wrong thing highlighted. This dot x location plus equals dx, which is negative 0.5, so 3.4, and then this dot y location plus equals 1.3. Let's make the math hard on this one. 7, 8, 0.8. So we're moving that object by those values. That's a good example, by the way, of a mistake you can make. If you have 0.7 here, I don't care. As long as it's clear that you trace through all of the concepts of 116 properly, called the right method for inheritance would be the big thing here. As long as you did that, I don't care if you make a simple math error. Okay, and then that's the end of this method. We go back to the main method. At the end of that, cross out the main method. And that's our final trace. So the two big things we saw is the superconstructor is always called. When you create an object of a type that extends another type, the superconstructor is always, always, always called. You better have two constructors for that object creation. If this constructor is missing, that's an easy autofill. That is not a minor mistake. That's a core CSE116 concept that is explicitly being assessed on that trace. If you miss your superconstructor calls, that's it. You fail that trace. And every semester I have some students who will take these traces, take every opportunity for the traces. In the fall and spring, they have 3 chances at each concept. It's just a different structure, but they have 3 chances. And on the 3rd chance, they're still not adding their superconstructor calls. Unfortunately, that's an F in the class. They don't finish the learning objective. Don't forget your superconstructor calls. And the other thing we're looking for is which method is called when a method is called, knowing that the use method was from the weapon class and that the move method was from the game item class. If you get those 2 things down, and you understand the other basics that we already covered, like references and just general constructor calls, how instance variables are updated, the keyword this, you're going to do absolutely fine on the OOP tracing. Those are the big key things that you need to know. I'd say references, the keyword this, superconstructor calls, and resolving which method is being called. Where to find the code for a method. Okay. And that's that trace. Okay, we got a few more slides here. So let's jump back to the slides and talk about the object class. Now that we've talked about inheritance, we can explore some features that we've seen in Java. We've experienced these, but we weren't prepared to really understand how they worked yet. So let's talk about the object class. So every single class in Java extends the object class. So if you write a class, so there's a few things to unpack there. If you write a class and you don't explicitly extend anything, like our game item class, we didn't type extends any class. If you don't explicitly extend a class, then you implicitly extend the object class. So this Java adds this for free. These 2 classes are identical. They have identical behavior. One of them just is explicit about its object extension. The other one is not. But both of these classes would extend the object class. And extension and inheritance is transitive. So when we have a health potion that extends game item, which extends object, indirectly the health potion class also extends the object class. So as a result, every single object in Java has the state and behavior of the object class. every single object ever has the state and behavior of the object class. So what's in there? So why would we ever care about this? What's in there? Well, two that we've used already, I think the only two we'll end up using, is toString and equals. With linked lists, when we moved to linked list of doubles, I had this big talk like we kind of cheated by using the equals method. How do we even know that method exists when we're calling it through a type parameter? We don't even know what type the object is. How do we know it has an equals method? We did the same thing with toString. That one I think was implicit, but we use string concatenation, which does call toString. How do we know the object that we're dealing with and the type parameter that we have has these methods? Well, because even though we don't know what type it is, we know it extends the object class, and object class does define these methods. Therefore, every single object in Java will have at least these two methods, toString and equals, and a handful of other ones that aren't relevant in 116. But these two we've already used, and used the feature that every single object ever has these. And then we wanted to find the minimum of a linked list of doubles. We couldn't do that. We had to actually explicitly have a linked list of doubles and then use the less than operator. Less than is not in the object class. You can't just ask anything, are you less than some other thing? So everything extends object. An object has toString and equals. Therefore, every object has a toString method. Every object has an equals method. We don't necessarily know what the methods will do before looking through some code, but we do know that they will exist. So we can call them. Okay, and moving on. So that's inheritance, that's the crux of it. But we have one pretty big issue, is that sometimes we don't want to inherit everything from a class. So let's talk about overrides. Ooh. Anybody have questions at this point? Okay. Let's keep on trucking. So we saw that we have inheritance where we can inherit all of the state and behavior from another class. We use the keyword extends. And that means give me all the state and behavior, all the instance variables and methods from this other class and add it to the class that I'm writing. So that's inheritance. But what if we don't want every single piece of functionality? So say we add this use method to the game item class that's just going to print out item use. Just some generic item was used. Maybe it would remove that item from a player's inventory and have some basic behavior of using an item. But in the base class, we can't really do much with it. In the super class, we can't really do, I didn't define base class. Pretend I didn't say that. But sometimes these are called base classes. This use method is going to be inherited by all of the other game items. But what if we have a game item that doesn't want to just say, yep, I was used? We want actual behavior from our items. So we don't want to just inherit from game item and take all of the state and behavior. We want to change some of that behavior specifically. We're not going to change the instance variables, at least not in 116. But we do often want to change the behavior of some of the methods. So here in the weapon class, what I'm going to do is override the use method. I'm going to override it to say, look, I know I inherited a method named use that takes no parameters, but I don't want that method. I don't want that definition. So I'm going to replace the definition of that method with my own definition, which is going to increase the damage output of a player. The player is equipping the weapon. It's kind of the context here. So we're going to override that method. And that will say, whatever you gave me, I don't care. I'm using this. Now, health potion doesn't override use. That means health potion is just going to use the inherited method, but weapon is going to use this new method that it wrote. And I'm using the override annotation here. So this at override is an annotation, meaning this adds some extra context to the method that I'm writing. I'm giving Java a heads up like, hey, this is what this method's all about. We're going to see this later. Actually, we've already seen it in problem set 0. If you look through the provided tests, we have the at test annotation to say that this method is a test method that should be interpreted by the JUnit library. So this is another annotation override. This gives Java a heads up that, hey, the method we're about to write is intended to override a method that we've inherited. Now this annotation is optional. So if I don't have this annotation, this code has identical behavior as when I do have the annotation. And personally, I like the annotation. I strongly recommend using the annotation because it makes your code a lot easier to read. Your intentions are very clear when you use the override annotation. But if you don't have the override annotation, as long as your method's signatures are identical, so you have the same name, parameter lists, parameter types, as long as everything's matching the method that you're overriding, it will still be overridden. You do get the override behavior without the override annotation. So they are completely optional. If you don't want to use them, don't use them. But the reason I recommend them is it gives Java a heads up. It says, hey Java, my intention is to override a method that I've inherited. And then Java, when it compiles your code, is going to check that for you. It's going to say, hey, you told me you were overriding something. If it doesn't find a super method with that same signature, it's going to flag you down and say, hey, I think you got something you got to look into here. Looks like you have a potential bug. You told me you were overriding, but you didn't actually override anything. And then you can fix that bug immediately without having some weird behavior. So say I mistype use, I accidentally have a capital S here. If with the annotation, Java's going to say, hey, there's no method with that name that you inherited. And then I go, oops, capital S instead of lowercase s. 2 seconds, my bug is fixed, and it's never caused any damage with the annotation. Without the annotation, what you get are two methods, the method that you inherited named use with a lowercase s, and the new method that you created, use with a capital S. And when you call this method, assuming you don't make the same typo, you're going to call use and just get item used and not get the damaging behavior of your weapon. And the program will just run. It'll be fine. Java's not going to be mad at you because that's something you can do. You can have methods with different names. There's no reason you can't do that. But you're not going to get the behavior you want. You're going to have a bug, and what's more, you're going to have a bug that's very difficult to find. You somehow just have to brute force figure out that you have a capital S there, which it's definitely going to take longer than the seconds that you're going to find this bug in using the override annotation. But that's the advantage of the annotation. It gives Java a heads up. The more information you can give Java, the better it's going to do at finding your bugs for you, so you don't have to spend, pull all-nighters finding your last bug. You don't have to do that stuff if you're giving Java a bunch of heads up. That's really the advantage of strong typing too. I don't know if I motivated strong typing that way this semester, but the idea of strong typing is Java can check all your types and say, hey, you told me there was supposed to be a double here, but you gave me a string. Like, maybe you should look into that because there's probably going to be a bug. Probably going to get some type errors. So it lets you know that right away. In IntelliJ, it'll even underline it with a red squiggle. Let you know right away that, hey, something's up. Because it knows what you're trying to do. And then if you don't do it, it'll say, hey, let's look into this. Let's figure this one out. So I like the override annotations because I make typos. And when I make typos, I want to be able to find them out right away. So I use the override annotation. And I don't have to, I don't have to think as hard as I would if I didn't use it. But if you're perfect and you never write the wrong code, go ahead, don't use it. It's up to you. It's a personal choice, personal decision. So this is the one. Yeah, I was getting my memory diagrams mixed up. This is where I have a memory diagram that we're going to bounce back and forth. We're going to do most of the trace, then come back to the slides, and then finish the trace. So we're going to have these two print lines right here. We haven't really talked about how to do this. You could probably intuit how it works without having to go through it explicitly. But we're going to go back to the slides to figure out exactly how those work before finishing this trace. So let's get what we know down. We can do everything up through these first 4 lines, the 2 use calls, the 2 constructor calls. And this one's a bit tougher to get all on the screen. I think this one is going to take some scrolling, unfortunately. Can I get away with a little smaller here? Oh, it still doesn't all go on the screen. Well, I'll size it like this until we actually hit a print statement. But yeah, this one's going to involve some scrolling. With these OOP traces, it does, you know, we just need a lot of code. I need a superclass and at least 2 child classes to be able to do anything with inheritance. So you can guarantee the OOP traces are all going to be at least 3 classes and then another class for the main method, or maybe I'll stuff the main method inside one of the other classes. Sometimes I'll do that. But it just by necessity has to be a lot of code. So let's start going through this. Main, just because it has a lot of classes. So main, we're creating a weapon. This is very similar to what we just did. It might be exact. I think it is the exact same constructor. But weapon, so we know how to do this one. Weapon, map the constructor. This is weapon. This is OX100. Our instance variables are from the weapon class, damage. And then we extend game item. So from the game item class, we get X location, Y location. And then I have 3 arguments. So I know I'm going to have 3 parameters to match, but let's get the arguments on screen. 1.3, 0.7, 100 damage. Our weapon got an upgrade here. We're calling new weapon. So I created my object, go to the weapon constructor, X location, Y location, damage, in that order. X location, Y location, damage. And we're ready to call the weapon constructor. The first thing it does is, as always, has to be the super constructor call. So the super class is game item. This is still OX100. There's no new object being created. I don't see the keyword new. It's not how super constructor calls work. It's a second constructor that's initializing the same object. It's just doing its part to initialize this object. So we have the game item constructor has X location, Y location. Getting the values X location, Y location from the weapon constructor stack frame, which are 1.3 and 0.7. And we're ready to run this stack frame. So this dot X location equals X location, 1.3, and then this dot Y location equals Y location, 0.7. This constructor's done. We hit its closing brace. So we go back to the weapon constructor. This super constructor call just resolved. So we continue with the next line. This dot damage equals damage, which is 100. 100 this time. Forgot my return arrow. And then that gives the reference of the object that was just created back to the weapon variable. All that we just did in the other trace. So I did go through it a little quick, but if there are questions, by all means, slow me down, ask questions, get them out there so we can, so we can all be on the same page and know what's going on. So health potion, we got health potion, same exact thing, not exact, it's a health potion, not a weapon, but same exact concept. OX200 this time. We have 3 instance variables, or sorry, 3 constructor parameters. It's the mistake I keep trying to emphasize and I said the wrong thing. But 3 constructor parameters. My code's wrong. Oh no. What part? What did I miss? Let me know what I missed. X location, Y location, increase. I'm not seeing what I missed quite yet. X location, Y location, increase. And our instance variables from the health potion class. Your code's wrong. What are you doing? And you gotta give me more context. What, I forgot. Oh, I do see one mistake. I forgot a variable here. Potion. And my return arrow. But you gotta give me a hint. Yeah, aside from missing that variable. Health potion. Weapon, game item, 100. Yeah, I don't see anything else that I might have missed, but yeah, let me know. Oh, thanks, Indominus. Health potion is going to get the health potion instance variable increase, and both of the instance variables from the game item class, X location, Y location. And then we're ready to run the health potion constructor, which we'll call the super constructor. So we have the game item constructor. We have two constructor calls to create a single object. The keyword this is the same. And we have our two instance variables of X. Man, I said it again. The two constructor parameters of X location, Y location, which are getting X location, Y location from the health potion constructor. Now, for these examples, we are just forwarding variables to the next constructor, but this could be anything we want. If we want health potions to always start on the X-axis, or on the Y-axis, we can set X to 0. Like that's something we're allowed to do, but we're going to do the basic thing of forwarding these variables to the next constructor. So we get 10.0 and 0.0. We're ready to run the game item constructor. Initialize X location. This dot X location equals X location, which is 10. And this dot Y location equals Y location, which is 0.0. This constructor ends. We go back to the health potion constructor. This dot increase equals increase. So we get 6 initialized here. This returns and gives OX200 back to the potion variable. So that's our two constructors, 2 times where we call the super constructor. So 3 times total you've seen that. Don't forget your super constructor calls. Never ever forget your super constructor calls. They always happen. Very important to know, just in general when you're programming, like knowing how your objects are being initialized when you use inheritance, knowing that that super constructor is being called. Very important to know. That's why we harp on it so much in this class. And next we have 2 use method calls. So here we actually have some choices. We have 2 different use methods. So here we do actually have an opportunity to mess this up. We have to make sure the right use method is called for each one of these method calls. So let's do that. Let's move my face here. We're not going to need another object. I'll hang out right here on the heap. And then we have a use method call. It's weapon.use. So weapon.use OX100 is the context. OX100. So when we call the use, and we have no arguments, so we know we're looking for a parameterless method. So to resolve which method is being called, we're going to look at the type of the calling object. Calling object is OX100, which is of type weapon. We always look at the object type. The object type. I emphasized that last time, I'll emphasize this time, I'll emphasize it again. The distinction, which I'll foreshadow Thursday with polymorphism, the distinction and the other choice you might have, the other thing you might try to do is look at the variable type. We never look at the variable type. With polymorphism, the variable type and object type can be different. So when we get there, just always look at the object type, ignore the variable type, and then when you get to polymorphism, you don't have to do anything different. Always look at the object type on the heap. So here we have weapon, so we're going to look in the weapon class for a method named use, and we find it right here and we call it. So damage dealt this dot damage is 100. That's the method that's called. Method returns. It's a void return type, so it doesn't return anywhere or anything. But this is the method that was called damage dealt. Now notice nowhere in there did I mention the override annotation. If you find a method with the signature matching the method that you're calling, that's the method that's called. Like that, you found it. Nothing else to do. You never check if the override annotation exists. The override annotation is only to help you find your bugs and typos that you may have made along the way. So it helps you write the code, but when you're tracing the code, the override annotation doesn't do anything at all. Doesn't do anything. This is when do we? Oh, I think that's testing lecture where those slides ended up talking about compilation versus interpretation. I'll do a very brief one with Java. It takes a pass of all of your code, your entire project, and compiles it, which is something that doesn't happen in Python in 1.15. So Java will double check all these things during compile time to make sure that your code is relatively bug-free. You might have logical errors and come up with the wrong answer, sure, but you won't have, well, you can still, but you won't have as many errors that can crash your program. Where in Python, it's easy to write errors that crash your program when it gets to that line of code. If you forget to put str to convert your int into a string before concatenating strings, for example, that program runs until it reaches that line and then crashes. Java is going to do a bunch of compiler checks and look for those types of mistakes all throughout your code before the code runs. And if there are any compiler issues, it flags you down and says, hey, look into this. The override annotation is a flag for the compiler. So after compile time, the override annotation doesn't do anything. If your code compiled, the override annotation already did its job. It helped the compiler look through your code and look for any bugs. But by the time your code's running, the override annotation has no effect. During your traces, that's at runtime, not compile time. We're tracing through the actual executing code. So anything that only matters at compile time doesn't matter during your traces. Override is a compile time flag, compile time annotation, so it doesn't have any effect on our traces at all. Same thing with all types except for object types. This is why object types are the only types we put in our traces, because every variable type, whether it's a local variable, a parameter, or an instance variable, all of our variable types don't matter at runtime. They're checked at compile time to make sure that all our types match up. But if our code's running, the compiler already did its job, and there's nothing left to check for types. So adding the types in our traces wouldn't change a damn thing in the execution of our programs. Wouldn't change anything if we added all the variable types. The object types do need to be there for polymorphism reasons. Well, actually, we see it already. To resolve which method is being called, you need to know the object type. But variable types, not so much. Don't need to know them. Because they're all checked at compile time. This is why Python can't be strongly typed. There's no compiler, so it wouldn't make sense to be strongly typed. You would have all these types everywhere, and they would never be checked. It does, not to get too sidetracked, this will be the last thing. Python does have what's called type hints, where you can say this variable is supposed to be this type. It won't be enforced by anything, but it can help your IDE, which in that case would probably be PyCharm, which is the IntelliJ equivalent, but with Python. It'll give PyCharm or VS Code or whatever you're using a heads up, so it can flag you down similar to how a compiler would and say, hey, you told me this was supposed to be this type, but I don't think it's going to be. The code will still run. It might crash if you have a type error, but you can get those, you can give a hint to whatever IDE you're using so it can help you keep your code bug-free. Java, it's built into the language. We have to specify all our types. Because we have a compiler that can do that, we're going to take advantage of that feature. And strongly typed languages, you might not really appreciate it now, but strongly typed languages are, I guess I have to qualify this with in my opinion, but in my opinion, way better than loosely typed languages, because it's just harder to write bugs. There's a certain type of bug, the type error bugs, that you pretty much just can't write, which is handy because, again, unless you write perfect code, you can benefit from type checks like that, and the override annotations, all the things like that. Anything that makes it easier to find bugs. If you've ever written a bug, if you've written a bug and took hours trying to chase it down and figure it out, then you need to love all these topics, all these concepts. It makes it harder to write bugs. Okay, and then finally, let's get back on track here. Potion.use. So this is Potion OX200. So now we have to resolve this method call. We're calling it from OX200, that's health potion. So we look in the health potion class. We're looking for a method named use. We do not find it, so we continue our search in the game item class. Game item does have a method named use that takes no parameters, so this is the method that's called, and we get item use with no actual functionality. No healing functionality because we never overrode this method. We didn't define our own use method in health potion. We just used the inherited method and get that default behavior. Now notice when we call this on health potion, we don't find use, so we go to the superclass. But with weapon, since we do find the use method, we never look in the superclass. We never even know, like technically weapon has two different definitions of the use method, but we never find this one. It inherited this method, but we can't use it anymore because we overrode it with this new definition. So whenever you have an object of type weapon you call use, you get the definition that overrode the superclass definition for that method. Okay, then we got to go back to the slides, talk about our toString calls. Print line will implicitly call toString. I'll make this explicit in tracing for the midterm and final. If I want to put any toString stuff on the midterm or final, I'll have an explicit weapon.toString call because I've had too many students fail traces because they forgot that this will implicitly call toString. And I got sick of harping on it and said, you know what, let's just make it explicit. Okay, so let's jump back to the slides. Talk about toString. And then come back to the trace. Okay, so we saw that every class in Java extends the object class either directly, indirectly, explicitly, or implicitly. One way or another, every object in Java is going to get all the behavior of the object class. State too, but I'm pretty sure the object class doesn't have any instance variables. But all the behavior. Today we want to talk about toString. So we get this toString method in every single class, but what does it do? So here it is. This is a short snippet from the actual object class. You can go to the object class. It's downloaded on your machine. It's accessible through IntelliJ. You can go to the object class and take a look at what it is, and you'll find a toString method that looks like this. This is the actual toString method from the object class, and this is what everything inherits. So this is that weird behavior, because we did talk about toString before. This is that weird behavior that toString gets, where it's the fully qualified class name, meaning package and class name, the @ symbol, and then the hash code as a hex value, which last time I said it's a random, at least random to us, hex value. And it's a pretty meaningless value to us. It can be thought of as the reference to that object, but it's obfuscated through lots of layers of Java goodness. So if we have a health potion and we call toString on it, what we do is the same thing we've done before. We go through our progressions. So if I call toString or print line on an object of type health potion, the object is type health potion. I'm going to look in the health potion class. I'm going to look for a toString method. I don't find it. So I'm going to look at the game item class. I'm going to look at its superclass and look for a toString method. And I also don't find it there. But I can continue my progressions. You can have long chains of inheritance, and you continue your progressions through the entire chain. So game item doesn't explicitly extend anything, which means it implicitly extends the object class. So we move on with our progressions to the object class and look for a method named toString. We find it right here, and this is the method that's called. So we get that toString behavior, that default behavior, because it's inherited from the object class. So if we don't override the toString method, this is the behavior we get, which is actually pretty dumb. This isn't what you want to be printed to the screen. Like it's just not. It's a really dumb thing to print. It can sometimes be helpful if you want the name of the class, but at that point, like you can just call getClass.getName, and there's an implicit this dot getClass.getName. GetClass is also a method in the object class. You can call that directly if you really want the name, and the hex value, the hash code really isn't interesting to us. And that's just not just me saying this, the official documentation, if you go to the object class, I removed it for the slide, but the official documentation says, you should really override this method because what we gave you isn't very useful. Like you don't want this, but they had to give us something. That's what they chose. They just gave us something, but they're like, you don't want this. Just override it. Please, this method only exists to be overridden. So let's override it. So let's rewrite our classes to override the toString method. And what we can do is override it in just the game item class. The game item can add the location information. That's all it really knows is location. So we can add location and have it print out X and Y values. And then when we call toString from a health potion, we don't find it in health potion. We go to game item, we find it here, call this method, and stop our progressions so we never make it to the object class. We effectively covered up the default behavior from the object class. And notice I'm using the override annotation right here. In the next example, I'm not going to use the override annotation because we can override this again. So I'm going to override toString in the weapon class, but here I'm not using my annotation, just to emphasize that we get the same exact behavior. Just don't forget to capitalize your S in this case. If you don't capitalize that S, or if you add a parameter here, change the return type, you're not going to get your override anymore. So as long as I type everything exact for the method signature, this will override the inherited behavior. So if I have a weapon and I call toString, I find toString here, I call it, and I don't ever look at the game item class. Once you find the method to call, your progressions stop. You don't do anything else after that. So even though weapon has 3 different toString methods, the original one from the object class, the one it inherited from game item, and the one it defined itself, has 3 different toStrings. So which one's going to be called? Well, it's the first one we find when we go through our progressions. We start in weapon, we find it, stop the progressions. That's the one that's called. End of story. With health potion, we're doing something a little bit different. One new thing here is that it's very common that when you're overriding methods, you don't want to 100% completely replace the definition of a method. Very often what we want to do is expand the functionality of a method. So we want to get all of the inherited behavior, but also add more behavior to it. So to do that, what we can do is use the super keyword and call the method that we're overriding explicitly. We can say, hey, from the super class, so let's jump up to game item and call toString. So we get this method call, and then we want to add more functionality onto it. I'm just saying this call was from a health potion, so not doing anything super interesting here. But if we want to add functionality to an inherited method, that's what we do. We'll call the inherited method and then add more logic to the method that we're overriding. So we effectively add functionality instead of completely replacing functionality. So a very handy thing to do, very useful in a lot of contexts when you're using inheritance. And let's do another memory diagram. But really we're continuing the memory diagram we already saw, and this will be the last thing for this slide deck. So let's jump back here, full screen, and get these print lines. So print line will implicitly call toString. So we have weapon.toString effectively. So weapon.toString from OX100. So this is OX100. And we got to figure out what's being called. What method is being called, because we have 3 toString methods in our code right now, and a hidden one from the object class. We got to figure out what's being called. So this is an object of type weapon. Always look at the object type, not the variable type. Don't look anywhere else. Look for your object type on the heap. It's why we put the object types on the heap, so we know what methods to call. So we look at this class matching that object type. Weapon, we look for toString, we find it, and that's it. This is the one that's called. So we have a local variable out that is getting weapon damage this.damage, which is 100. Then we're returning that. We're not returning into a variable. We're returning into something in the print line, probably a variable inside print line. Print line's internal to Java, so we were not tracing that. So we have no return arrow here, but we do have to know that that's going to be printed to the screen. Whatever we return here, print line will print that to the screen. So we get our third print statement. We're going to print weapon damage 100. And then go back to the main method and do the same thing with potion. So potion is OX200. So we have toString being called where this is OX200. That's an object of type health potion. I'm going to look in the health potion class for a toString method. I find it right here, and this is what I want to call. And the first thing I have to do here is call the super class's toString. This technically doesn't return directly to a variable, so I'm not going to do a return arrow, but this will, I have to kind of keep track of where this is going to return. But we've got to resolve this method call, super.toString. Super is a keyword that can be used in place of the super class name. So this is like kind of like saying GameItem.toString, but it's not calling it through the class, it's calling it through an object, so that's kind of a little weird. But it's going to the GameItem class and looking for a method named toString. So we go to the GameItem class, and then we restart our progressions. So we'll find toString right here. We're going to hit this method call. But if we didn't, if GameItem didn't override toString, we go through our progressions again, go to the object class, and get our default toString behavior. When we have super.method call, we go jump up to the superclass and then continue our progressions until we find an appropriate method to call. So we have out, and we got quite a bit to keep track of. X, oops, I almost made a mistake there. So we have toString from the GameItem class. We don't annotate this in our traces. If you want to do GameItem.toString, just to make it abundantly clear, that's fine. But in your traces, you don't have to have the method type at all. We'll know by the keyword this, and looking at your trace, we'll know if you called the right methods or not. And when you have a super call like this, just like the super constructor call, this is still the same context. We're still talking about the object that made the original call. And this will return, what it returns is x colon space this from this stack frame. It's the same reference, but this dot x location, so 10.0, and then a space y colon space this dot y location, which is 0.0, and then that's going to be concatenated with this space dash space health potion and then in brackets the amount of increase. So this dot increase, which is 6. Get my closing quote. So this is what toString is going to return. That returns to the println method. That's what potion.toString, which is internal to println, is going to return, and then that gets printed to the screen. Whatever toString returns, that's what println is going to print. Then we hit the end of main, end of the program. So if you're good with this trace, if you could go through this whole trace on your own, you're in really good shape for the midterm and probably won't have to take the final if you're doing good with this one. Polymorphism doesn't add much more to the traces. We'll talk about it. The big punchline is ignore types, which we already do. So if you go through this the same way I did, polymorphism isn't anything new. So with this one, so if you didn't understand everything there to the point where you could go through this trace on your own, I would like your questions so I can help clear up any confusion. Somehow we're making really good time. I feel like I don't get this far in the regular, I shouldn't say regular, but in the fall and spring semesters, when these are 3 separate lectures. I feel like both of these usually go over. And this one I think is pretty light. We'll have some time. I won't be able to resist going through some debugger practice since we'll have a little bit of time. Okay, let's keep pressing on. All right, am I looking at the clock wrong? 11 to 11:50. Yeah, we should be at 12:40. I expect us to be at like 12:50 right now. I don't know. I feel like I went slower too. I don't know. Usually got my timing down. Okay, so let's talk about the next topic: abstract classes, abstract methods, and interfaces. These are brand new things. Or maybe we'll just end early today. I mean, I'm getting through everything I need to talk about. I'll leave it up to y'all. If let me know in chat. So methods can be abstract. This is a really weird thing to see at first. I'll try to do it justice why we do this. I won't be able to fully get you to appreciate this until we learn polymorphism, so I will circle back to this topic. Some of the polymorphism slides talk about abstract methods again. But for now, you'll just have to trust me that this is useful, and let's talk about the mechanics of how it works. So if you have an abstract method, this is a method with a signature, meaning you're defining the name, the parameter list, including types, and the return type, but you just cap it off with a semicolon and don't give it any body. You give no definition for this method. If you don't give a method a definition, it's abstract. You have to label it with the abstract keyword. And if your class has any abstract methods, the class itself must be abstract. So you have to have an abstract class if you have any abstract methods in that class. And the big feature of an abstract class is that you cannot create objects of abstract types. Because if you could, what would happen if you call an abstract method? This method has no definition, so what should happen if you call it? Like, what would you expect to happen if you call an abstract method? You call a method that has no definition. For this, the example on screen, you might say, well, it returns void, just have it do nothing, which is fine. But what happens when we have an abstract method that returns a double or a string or a reference to a player or an array list of doubles? Like, what happens when we have methods that have return types? What should we return? It's not clear what should happen, So Java just says, no, you can't call abstract methods. Period. Can't call abstract methods. It's not allowed. You have a method with no definition. What do you think you're doing calling that? Like that can't happen. So if you have an abstract method in a class, the class must be abstract. And if you have an abstract class, you cannot instantiate that class, meaning you cannot create objects of that type, meaning that I cannot anywhere in my program say new game item because game item is abstract. You can't create an object of an abstract type. It's not allowed because if you could, then you might be tempted to call that abstract method, and then what should happen? So if you have an abstract method, your class has to be abstract. If your class is abstract, you cannot create objects of that type. Can't happen. Which begs the question, why the hell would I ever do this? Let me just give my methods definitions, which we can't fully. I'll preview polymorphism a little bit just to get it out there why we would do this, because it seems silly at first. It should seem silly. Why would we ever do this? Let's just give your methods definitions. But these abstract classes only exist to be inherited, meaning that if you have an abstract class, the only useful thing to do with it is extend it. So here with game item, that's pretty convenient because we actually don't want any game item objects. Nowhere in my code do I want a game item object. Because what happens if you're playing this game? You're playing the game, you're having a good time. Hey, there's a health potion, let me equip that weapon. Oh, a bow and arrow, let me shoot that. What happens when you come across a game item? What is that? Like, what's a game item? Oh, I want actual tangible things, not game item. Like, that doesn't make sense to me. I want a bow and arrow. I want a sword. I want a health potion. I want a mana potion. I want a spell book. I don't want a generic game item. I don't know what that is. It's probably going to be a glitch. It's going to be like getting Missing No as your Pokemon, which actually is a bad example because that's pretty cool. But it's like we have a type that shouldn't really exist. What do? We don't want that. And we can actually make classes abstract even if they have 0 abstract methods as just a way of saying I don't want any game item objects in my game. I just don't want it. Create health potions, create weapons. Don't create game items directly. Making it abstract prevents anyone from calling the game item constructor directly. They can only call it as a super constructor call. Can you make the constructor private instead so no objects can create it? But then you wouldn't be able to call the super constructor because private means you can only access that code from within that class. So health potion wouldn't be able to make the super constructor call. So we can't quite do private. We do have another option. We can make it protected, which would limit how people can instantiate it, while allowing child classes to call that constructor. But abstract is the more powerful, just abstract, and nobody can create objects directly of that type. Only objects that extend to this type. Protected, since I mentioned it, the keyword protected means that method can only be accessed from classes that extend that class. So any child classes of that class, even if it's like 3 layers deep, X extends Y, extends Z, extends W, and W has a protected method, that method can be called by X, Y, and Z. And any classes in the same package as that class. So if they share a package, then you can also call the protected methods and access the protected instance variables, which is why that can leak some functionality and information if you use protected, because you got to be really careful about what else is in that package. And for some reason, Java doesn't have an access modifier that says only child classes. Kind of seems like a strange omission to me, but it's the way it's always been. So abstract prevents anyone from creating objects of type game item, and then we'll extend this class. But when we extend the class, when we inherit all the state and behavior from this class, we also inherit an abstract method. We inherit this abstract use method, which has the same problem. Like we can't, if we have health potion extends game item, we can't create new health potions anymore. So we have 2 choices. If we have a class that has any abstract methods and we extend it, we have two choices. We either implement the abstract methods, and by that I mean override the abstract method. So I can override the use method, give it a definition, and now it's no longer abstract from my child class because there is a definition. When I go through my progressions, I find that definition, call that method, and I never find out that I inherited an abstract method. I never find out that it was abstract because I gave it a definition. The other option is for the class itself to be abstract. So if I have a class that extends game item and I'm like, I don't know what use should do, I can just have that class also be abstract because it inherited an abstract method. If I don't want to give it a definition, I'll have that class be abstract. The weapon class is a good candidate for an abstract class. Have public abstract weapon extends game item, because what is a weapon? Same thing, similar to I'm playing a game and I find a game item. Like, what is that? Also, what is a weapon? Like, it's just some weapon. I don't want a weapon. I want a sword, a bow and arrow, blanking on examples there. A boomerang. Like, I want a specific type of weapon. So weapon itself might be abstract as well. It would be a good candidate for another abstract class. And then each specific type of weapon that extends weapon, bow and arrow extends weapon, will implement the use method to say spawn an arrow item that extends game item and give it this trajectory when based on which direction the player is facing. You would have that specific functionality in the use method in the bow and arrow class. We can take this a step further. We can actually I want to talk about this a little bit more. So why we would use abstract methods? I want to at least touch on this. The answer is going to involve polymorphism. For now, having an abstract method in a class guarantees that that class knows that that method exists. But when we don't have any default behavior to give it. So like the object class's toString method could be a good candidate for an abstract method because the default behavior is so dumb. Like, we could just make it abstract because we want the functionality where every object in Java has a toString method, but we don't necessarily know what it'll do. It depends on overrides, whatever method you use that overrides to the toString method. So they could make it abstract and say, you decide what toString does, but since it exists in the object class, then we can call it from any object, which is a very powerful thing. To be able to have a type parameter and call toString, it's a very convenient thing to be able to have, to be able to do. But the fact that we can take anything and put it into a print line call, we don't necessarily know what we'll get, but it's a very powerful thing. That only happens because toString exists in the object class, but it could be abstract and just say, hey, override this. Instead of saying we recommend that you override this, make it abstract and say you have to override this. I'm glad that they don't do that because that would mean every single class that we create in Java would have to have a toString method. That means from day one, hello world in Java would have to have a toString method. So I'm glad they don't make it abstract. But that would be the use case for abstract, is you want the method to be known to exist to a wide audience, but you don't have a good default behavior for that method. So you just say, okay, the use method exists. Every game item can be used by a player, but instead of having print line item used as the default behavior, we're just going to give you no default behavior because every specific game item needs to define what it does on its own. We're going to make you implement that behavior when you write those classes. So we can take this a step further. We can have what would be classes or abstract classes that only have abstract methods. And if we do this, we can call them interfaces. So instead of, this is our first non-class type, and the only non-class type we'll see, is interface. So we can have public class, public abstract class, but now we can also have public interface and define an interface at the top level. So this would be in a file named comparator in the directory structure matching the package, just like a class. It exists at that same level, but it's not quite a class. It doesn't have a constructor, it doesn't have instance variables or anything. In fact, it cannot have them. So no instance variables allowed, no constructors are allowed, and no methods with definitions with an asterisk. There's a new, well, it's not new anymore, but there is a keyword that didn't used to exist at some point in time called default, which does give you, allow you to define abstract methods. Aside from this asterisk right here, I'm not going to mention that again in 116. We're going to pretend they don't exist. But it is a thing. You'll see somewhere in your career. You'll see those. So don't panic when you see that. It's giving an abstract method a default definition, which can be dangerous for what I'm about to explain. So interfaces only have abstract methods. That's the only thing they have in them. There's an asterisk to that too, but I don't want to get too sidetracked right now. Actually, go to IntelliJ and show that. So we can only have abstract methods. But why would we do this? Like, it kind of seems silly to... I'm covering up this bullet point. I don't feel like moving my face again, but it says this avoids the potential of multiple definitions for the same method, which is what I'll explain here. So we would create an interface because you can only extend one class. You only get one shot at extending a class in Java. So you can only extend a single class, a class or abstract class, one only, and exactly one, because if you don't extend anything, you extend the object class. So you always extend exactly one class in Java. The only exception to that is the object class itself doesn't extend anything. The madness has to stop somewhere. But you can implement as many interfaces as you'd like. If you want to implement 100 interfaces, go for it. You can implement as many of these things as you want. So what this avoids is multiple definitions for the same method. If you could extend multiple classes, and those classes are allowed to have what we call concrete methods, which are regular methods, methods that are not abstract. What if you inherit the same method signature from two different classes that have two different definitions? When you call that method, which method should be called? Because you don't just go to the superclass anymore with your progressions. Now you have two superclasses. Which one do you go to get the definition? Which one should be called? Which one should be used? I don't know. Java doesn't know. Java doesn't define this. What Java says is, well, you just can't do that then. It says you can only extend a single class. But since interfaces can only have abstract methods, you don't have the same problem. If I have an interface that says, I have an abstract method called compare, so you have this contract that says you must implement the compare method or be abstract. And you implement another interface. Oh, by the way, use the keyword implements to distinguish between extending a class or implementing an interface. So if you implement another interface, if you implement comparator of integer and then another class that also tells you, hey, you need a compare method, it returns a boolean, takes two values of type t, and gives you the same contract. You have to implement this. Well, big deal. We already had that contract, and we didn't have any definition that's going to conflict with what we do. We're going to implement that method once, and if it satisfies multiple interfaces, that's fine. Who cares? That's perfectly fine. There's no question of what method's going to be called. If I inherit two abstract methods from two different interfaces, or even an abstract class too, two interfaces and an abstract class, I have to write that method. I write the method once, and whenever I'm calling that method, I go through my progressions, find the method. Doesn't matter if I'm calling it in relation to one of the interfaces or the abstract class. I'm always going to find the same definition, so there's no ambiguity. So that's why you can implement as many interfaces as you'd like. No competing definitions for your methods. And then you go through the progressions just like normal. And your interfaces don't have any concrete methods, so your progressions never go to the interfaces. You're always going to whatever you extend. So if you, say, have an object of type int decreasing this example, and you call toString on it, you're going over to the object class to be able to resolve that toString call. Because I don't extend anything explicitly, I implicitly extend object. So there are a few things. As always, if there are questions, slow me down. I'll jump back to something. There are a few things. Let's look at. I don't even have any interfaces here. We'll talk about the comparator interface on Thursday. I didn't really talk about this type parameter syntax and stuff. We'll talk about that the last thing we do on Thursday. So we'll circle back to that. But I'll use this usable interface where if I want an interface that says you have a use method, the use method will exist. First of all, the advantage of doing this is I can write code, and this is going to foreshadow the next thing we'll do. I think it's in the player class. Is that we can have the instance variable. We can have an array list of usables, which is an array list that stores objects of any type as long as those types implement the usable interface. And then when I'm working with my inventory, I know that my inventory items are going to have a use method. So if I have a variable of type usable, I don't even know what object is being stored in that variable, but I do know it has a use method because that's what the usable interface guaranteed. Usable interface said anybody who implements me must implement a use method that takes a player. So I know that that method exists. I don't know what it's going to do yet. It's up to each class. So health potion is going to extend game item like before. We can also implement the usable interface. And then I do have the contract to override the use method. Here I can optionally use my override annotation. But I don't have to. Because as long as the signature matches, then we're good. If I don't have my override annotation, and I have, say, a capital S here, with an abstract method, this is actually a bit more convenient. If we try to run this, does game item have a use method? Ugh. Well, I have to add a typo here too. So actually, let me just make both points. So when I run this code, I need a code that calls the health potions use method. Player use all inventory methods. This example's a little big, but we'll pick out the piece that we need here. But, I just wanted this to be simple. Let me add my print lines. Use from game item. Use from health potion. So let's rerun that code. We are using all of our items. And we got use from game item twice, which means that my weapon doesn't override use. Oh, it does override use. Oh, I must be calling from two different health potions. Yeah, we created two health potions and called use all inventory items. The weapon isn't printing anything to the screen, so that means we got the game item behavior. So when we called use on a health potion, we looked for the use method in the health potion class. We did not find it because this has a capital S. So we continue our progression to the class that we extend, the game item class. And here we find the use method here, and we end up healing the player. This example is so weird. I expected this to be the end of lecture, so I didn't review these, if you're wondering. But we get some bonus stuff to hopefully make this more clear. And we're going to call this method because we didn't override this method at all. If we mess up this one too, if we have another typo here, we're not even going to be able to run this code. Because Health Potion has a contract. Health Potion, it implements the usable interface. The usable interface says you must implement the use method, but it never did. It never overrode the use method because I have this capital S here. As long as I fix my typo in one spot, now I fix it in the health potion class, health potion.use, It exists, so the usable interface is happy. And then when it's called, it's going to be from the health potion class. So now we have the health potions use method. And for good measure, we might as well fix this. Oops, actually did it again. Even when we fix that, the game item method is never going to be called. It's just the health potion use method. Okay, that was a little bit of a side test. What I really want to show is in the slides, I had code like this. It was the comparator and the compare method. But the same idea here. We have void use and then takes a player. But I didn't use the keyword abstract at all in this. I said interfaces can only have abstract methods, which is a little bit of a lie that I'll explain soon. But I also didn't use the keyword abstract. So let's add that and just see what we get. Let's actually add abstract public. So when I add these keywords, they get grayed out by IntelliJ. And if I hover over it, it says abstract. You don't need to tell me it's abstract. Also, you don't need to tell me it's public. Because if you write a method in an interface, it has to be an abstract public method. So there's no point in telling me it's abstract and public. You don't have to tell me. You told me that by creating an interface. I know all the methods have to be abstract and public, so we don't have to repeat ourselves. If it's in an interface, it's abstract and public. So this looks like just a method with no definition, but it is in fact an abstract method. And if you go into a usable class, we can also do something like this, which sure looks like an instance variable. You cannot have instance variables in interfaces. It's not allowed. So what the hell's going on? Like, what gives with this? It's kind of strange that we can do this. So it's doing the same thing that it does for methods. We can use this syntax, but there's a lot of implied keywords here. One, this is public. It's also final. It's also static. So we can create public, final, static variables, meaning constants that belong to the interface. We can't create instance variables that refer to that belong to instances of type usable, because just like abstract classes, usable has an abstract method. You can't create an object of type usable. It's not allowed. So we just can't have instance variables in interfaces, because then we'd have the same issue of multiple definitions. If we implement two interfaces and they both have an instance variable x, which one's used when we use x? Like, I don't know. But we can have static constants defined in the interface. But don't get confused and say, hey, Java let me type this. It looks like I have an instance variable. You don't have an instance variable. You have a public static constant is what that is. And since it's a public static constant, naming convention says name it with a capital X. Still tripping me up that I missed the time in by this much. No, we did everything. What I could be missing. So I guess let me know in chat what you want to see. I always like going through some debugger practice if you want that. Actually, maybe I won't leave that up to a vote. But let me know what you want to see. Probably just do debugger practice. Let's get back to the inheritance code. But if you want to see something different, let me know. I'll do whatever y'all who watch live want me to do. And if that is end early, I wouldn't complain about ending early too. Kind of low on energy today. But let's see. Actually, I'll probably just click around and find an example I really want to use for the debugger. Yeah, I'm not gonna be able to resist. I don't know where else debugger is gonna fit. Maybe in the testing lecture. But let's get some in here. So this is the code that we traced. So let's run the debugger and see that we can see all of the same information that we traced. This is the last one that we traced. So let's go through this. And what I want to emphasize is that the debugger will show you all of the same information that we trace. There will be a few nuances, so I want to highlight the differences, but it's really identical to what you're tracing. So I'm going to set a breakpoint and then run the code in the debugger. What that'll do is run the code until it hits a breakpoint. I can set these breakpoints anywhere and everywhere. For this lecture example, I'm going to set it at the first line of main. If you don't know where to put your breakpoint, put it at the first line of main. When you're debugging your problem sets and you have the bug narrowed down to a certain method call or a certain few lines in that method call, you would set your breakpoint right there so you can jump right to the relevant code. But here, I just want to trace through the entire program, so I'm going to start at the first line of main. And I'm going to run this in the debugger. And that's going to run my code until it hits my breakpoint and then give me all of the information of what's happening in memory at that point in time. So right now, the code stops before the line of the breakpoint. So right now, nothing's really happened yet. None of my code has executed. And we can see that args is on the stack, and it has a reference to an array of strings of size 0 at 472. If you want to trace your args, that's fine. It is technically always there. It's just a pain to trace. Like, I'm not gonna, it's tedious to have you add that to every single trace ever when we're never gonna use it in 116. So you're welcome to do that. You do have to create a new object on the heap for your string array that's not gonna have anything in it. And then args is a reference to that string array, but if you're welcome to do that if you want. You're more correct than the way we do it in 116. And whenever you see this at and then a number, you can think of this as our references, our OX100, OX200. What this means is that args stores a reference to this object of type string array. So that's what's actually stored in args. And if there's actually something there, we'll get an arrow and a dropdown, which will show us everything that's in that object, all of its instance variables. And I'm going to click this Step Into button. This is going to advance one line of code. So the next thing that has to happen is I'm going to go into the weapon constructor. So let's get into this constructor. And what I can see is a few things that happen. I have this weapon constructor, which is this init, means we're calling a constructor from the weapon class, and we're currently on line 7 in our package name. So in this stack frame, we can see this is a reference to some object at 476. This is the object that's currently being created by the constructor. It gives us a little note for that one. And then it tells us what the parameters are: X location, Y location, and damage, matching our constructor parameters. And this is a reference to an object of type weapon. And here there are instance variables, so I get this arrow. What this arrow means is follow the reference and show me the instance variables of that object on the heap. And right now, all the variables are 0. But we do have damage, X location, and Y location. We have all 3 of these instance variables: damage from the weapon class, and X location, Y location from the game item class. So we can see all 3 of those variables as part of this object. And when I do like int damage and don't initialize it, Java does have default values for every type. The default value for an int is 0, the default value for a double is 0. So these do actually get values. Again, if you want to trace your default values, your default initializations, that's fine, go for it, and then cross them out and when we initialize them. But that's another thing where we just treat them as uninitialized. In the traces in 116, we're always going to explicitly initialize our variables, so there's no need to trace that if you don't want to. I don't trace it in lecture. And then this tricky little thing, I don't like these personally. Whenever you see the glasses icon, actually I do when I don't. Whenever you see the glasses icon, what this means is that the debugger thinks there's a variable, an instance variable on the heap that's going to be of interest to you. Which is actually really handy, because this .damage is about to be initialized, so it's saying, hey, this .damage, it's 0, and it's showing us that without having to click on this arrow to see this .damage is 0. It just says, hey, by the way, this .damage is 0. With the glasses letting the symbol meaning we're going to peek into this object. The reason I don't like this is it's confusing if you're using this for practice, for traces, because it looks like this is on the stack. This is not on the stack. Whenever you see this glasses icon, that means that variable is not actually on the stack. It's just the debugger trying to be helpful and show you something that's on the heap that may or may not be of relevance to you soon. So the glasses icon means it's not actually there. It's an illusion. It doesn't go in your traces. So I'm going to do Step Into again. Let's get to the next line. It's always the super constructor call. That's what we have to call if we're going to have if we're going to have inheritance. So we have another stack frame. We're at line 7 of the game item constructor. And we see X location, Y location as parameters on the stack frame in this stack frame. And it's showing us this dot X location, this dot Y location. Those are not on the stack, but they are instance variables that may be relevant. And we can jump back to the other stack frame. If we go to the weapon constructor, we say we're initializing weapon at 476. If we go to the game item constructor, it's still the weapon at 476. So the keyword this stores a reference to the same object in the original constructor call and the super constructor call. So the super constructor, this is, if we're initializing OX100, it's going to be OX100 in the super constructor as well. And then we're going to initialize X location, Y location. So I'm going to run the next line, which gets to X location. It didn't run yet. X location is still 0. And then it executes. X location on the heap got the value of X location on the stack. And same for Y location. And then this method ends. The super constructor ends. This is where in our traces we would cross this stack frame out. The stack frame with this at 476, that reference, X location, Y location, those 3 values in that stack frame, we would cross out that stack frame. In reality, it actually does disappear. So that stack frame's gone. It's erased from memory, and the next stack frame we create is going to reuse that same location in memory as that game item constructor was using. So it's the same exact location. It is actually removed from memory. That's one big difference. In our traces, we will cross them out, so we preserve all the history. But in the debugger, it's going to show you what's actually happening. It is actually being removed from memory. And we'll initialize damage. It's currently 0. Initialize it to 100. And then return. So what the weapon variable gets, once I hit go again, step into again, weapon gets that reference at 476. Or OX100 would be in our traces. It gets a reference to the object that was created, and we can go over to the heap and take a look at all of the values for the instance variables for this weapon object. And for continuing debugger tips and tricks, we're about to create a new health potion. It's going to be the same thing. We'll call the health potion constructor, which we'll call the game item constructor, and construct a health potion. I don't really want to go through that same thing. I kind of do, but I want to show off this other feature. So if there's a line of code that you don't want to get into all the details from, it's a line that's going to create a stack frame that creates a stack frame and just does a whole bunch of business. What you can do is do the step over button. What this one will do is execute the next line of code in its entirety. Instead of going into new stack frames, it will execute the entire line of code and then continue on the next line. So if I do step over, everything, the health potion constructor, the game item constructor, all the initialization, all happened. I got conveniently 666 for my health potion. So I got a health potion where increase X location, Y location is exactly what it was in our trace. We would have those 2 constructors in our trace, but we just skipped it all. Especially helpful when you're debugging your code, you're writing problem set code, it's not working, you're not sure why, it's not passing your tests. It can be helpful to skip over the parts that you know works and more quickly get to the interesting parts where there might be a bug. Then we get to weapon.use. So weapon is 476. So this is going to be 476. And then we don't have any parameters, but again, we have the glasses. That means this variable doesn't actually exist. It's an instance variable, this.damage, this.damage 100. It's just showing us what that value is. We're going to print that to the screen. And we have this other tab, console. This is the usual view that you see when your program's running. We can see that damage.100 was printed to the screen, or this would be the I/O section of our memory diagrams. So we looked in the weapon class, found a use method, called it, and that's it. For potion, we're going to end up in the game item class. So we're calling game items use method at line 31 is where we're currently at, because health potion doesn't have health potion doesn't have a use method. Well, it does. Well, I get to make this point anyway. Health potion doesn't have a use method because we're calling a use method. We're calling use that takes no parameters. The parameter list has to match to resolve a method call. So when we go to the health potion class, we do find a method named use, and it has the right return type, but it takes a parameter. So this method signature does not match the method we're calling, so we didn't find the use method. We're not calling a use method that takes a player, we're calling a use method that takes no parameters at all. So we don't find one such method like that in health potion, so we continue our search to game item. When we look through game item, we do find a use method that takes no parameters and returns void, so this is the method that gets called. So if we look at our console and advance one line, item used printed to the screen, that's what the functionality of the health potion, of the health potion's use method. That stack frame's done. Then we get into our print lines. And notice that we did jump to the toString. The debugger is mostly pretty good about sticking with your code. So the print line method is on the stack. Like, we can see this code that's internal to Java. But we don't, and we can see the toString call right here. But we don't care about that. The debugger skipped all that and got to the point where our actual toString method is being called. But we do have 2 extra stack frames. We don't trace those in our memory diagrams. We don't really care about those. We're not looking for bugs in the print line method itself. We're going to, take it for granted that the Java devs have the print line method working after 50 years. I forget how long Java's been around, but forever, decades, that the print line method works. But it does call our toString method. We're not sure if our toString method works, so the debugger will, because if we're running the debugger, we probably have a bug, or we're teaching a lecture on the debugger. We probably have a bug, and that bug is going to be in code that we wrote, so the debugger is taking us to our code. Sometimes the debugger will get lost in these Java method calls. That's where you would hit this step out button. What that'll do is execute until the current stack frame ends and gets you out of there. So clicking that a few times usually gets you out of the Java internals and back to where you want to be. So player.setDamage. Oh, that's not what. Nope, sorry, toString. So out. This is our first local variable that we're creating. And strings are, so we write this in our memory diagrams. The debugger shows us the same thing. The debugger agrees with us that let's ignore that strings are objects on the heap and just pretend that out stores this value as a string. But if we take a look, we do see that this is a reference to an object on the heap, and that itself has a reference to a byte array somewhere else on the heap with the character codes for all the characters in the string and some extra instance variables. So there's a bit going on with the string class. We just pretend it's stored by value and call it a day. But the debugger will show you exactly what is going on. We have an array of bytes to represent our characters, our ASCII characters in this case. We'll just pretend it's stored by value and ignore those details. Return that, and we get right back to our code, meaning that was printed to the screen. And we get into the potion toString. Potion's toString calls super.toString. So super is game item, so we're going to jump to the game items toString. So we have 2 toString calls on the stack, just like we did in the trace. That's going to return this string with the location information. Then we're going to concatenate the health potion information to it. We have another string on the stack that we're going to pretend is a value, not a reference to an object on the heap, which has a reference to another object on the heap. Strings are, if we had to trace strings, it'd be just so tedious. And that gets printed to the screen in this format. Again, just like we did, looks like we nailed the trace, got everything, no surprises. That was everything that we traced through in the tracing tool. Then the main stack frame is crossed out. When the program ends, there's nothing left on the stack. There's no calls here, which means we have no references to any objects on the heap. They'll all get garbage collected, everything gets cleaned up. All we're left with is what was printed to the screen. Or if we have file I/O, that's where we would use files. If we want some persistence, we would have some file I/O. Okay, that's my debugger tutorial. Very useful. Like if you're struggling finding a bug on a problem set, the debugger can save you countless hours. I say that confidently because I've saved countless hours by running the debugger. There are certain bugs that I just would not have found in any reasonable amount of time if I wasn't using the debugger. But the debugger has a way of just slapping you in the face and saying, here's your bug right here. Look, that's not the value you expected at this point in time. Or this isn't the method call you expected to be in. For example, if I have, actually let's do this one. Let's do a little bit more complicated example. We have health potion, and say I have this capital S. And I want to know about this method call. I'm not getting the right behavior from this method call. If I'm really thinking, I'm going to put a breakpoint in the game item. Oh, I'm in the wrong code. So if I have this typo, and if I'm really thinking, I'm going to put my breakpoint in this code too, especially if I realize that this is the behavior I'm getting. I want to set breakpoints in the relevant locations. I want to fix my typo up here to make sure that my code compiles. And then go down to the player class that we were running earlier and run this in the debugger. So it's going to run until it hits a breakpoint. And what I notice is I hit the breakpoint in the game item class, and I can see there's no stack frame for the health potion. I have item.use. Item is of type health potion, and I'm calling a method named use that takes a reference to a player. I would expect to go to the health potion class, but I can see immediately the debugger's just slapping me in the face and saying, hey, you're ending up in the game item class. It's probably not where you want to be. Maybe you should look into this. So then I would immediately look at my health potion and say, oh, well, I don't have my override annotation for one, and I have a capital S here. Hopefully I catch that pretty quickly. But if I'm not using the debugger, I'm just like, why is my program broken? Like, why am I not getting what I want? Or in your cases, why is Autolab not coughing up points? Run the debugger, write some test cases. We haven't gone over formal test cases yet, but run the test cases that are provided. And if you're still not finding the bug, if you're passing all those but not in Autolab, you can still just write a main method even without either study the test cases we give, follow that structure and write your own test cases, or just write a main method. All the main methods will be ignored by Autolab, so you can put whatever you want in a main method as long as it compiles. You can put whatever you want in a main method. So write a main method, put a breakpoint in it, and trace through your code, figure out what exactly is going wrong. You can find your bugs significantly faster than without the debugger. All right, so and that's really everything I want to talk about, which I'm glad we did get a little ahead. I'm still wondering why. I usually nail the timing, but maybe I'm just disoriented today. But then I even got to squeeze in the debugger tutorial. Is there anything else anyone wants to see me demonstrate or me talk about or explain? I'll give it a minute or so. Do anything on demand, and if not, I'll instead of just making up more stuff and rambling through some code examples, I'd rather take requests. Oh, only 8 of you watching at the moment anyway. Hopefully everybody headed out to start the problem sets. And I'll have office hours at 1:30 to 2:30 today. So if you got questions, that aren't suitable for a lecture context, hop in office hours. All right. Interpret that as no requests. So amazingly, we actually will end early on a summer lecture. 20 minutes. I think this lecture might have gotten some content moved down here. I think that's the big change. But yeah, have a great one, everyone. I'll see everyone Thursday if I don't see you in office hours. Take care.